Right. עברית, אנגלית? English?
English.
English. Shaul just called. He's stuck in traffic. He hopes to be here in very soon. I won't say in a few minutes, but very soon. So he apologized and so be here.
10 points off.
הוא יאחר
Final grade.
בכמה
Okay,
דקות?
so תוריד לו.
אחלה.
Nice. Hey, I mean terrible. Traffic. It's by terrible meaning, man. Bye.
לא, אבל...
למה דווקא שני פאי K הרי? כאילו לקחת את הנקודות האלה.
כן.
יש את הנקודות של הנקודה K?
לא את הנקודות האלה, את הנקודות... כן, זה, וזה כפאי.
כן, לקחת כאילו זה, אבל לא הבנתי שני דווקא זה, כאילו זה גיטי?
כי אלה הסל... לא. אלה הסל נוטיפיקיישן. כן, אני מחכה אתה מחפש כסל לא. אני כבר לא זוכר מה אני צריך לעשות פה, אבל אני זוכר שאת זה... אבל
טוב, בסדר. אז רגע, אבל אכפת זה גם זה וגם
כן, עשיתי כאילו הנוסחה פה. כן, אבל אנחנו מעניין אותנו רק הראשון, זה כאילו פשוט נקפיץ. כן, זהו, בגלל זה לא היה כמו שהוא כתב, כי איך שהוא כתב, אם אני זוכר נכון, היה צריך הכל כאילו, גם אתה נתגלת כאילו, D בריבוע F ו-DR, גם ב-R מנוסחר C וגם ב-X מנוסחר C, ככה אני הבנתי, מאיפה שהוא כתב, ולא הבנתי למה.
זה לא קשור להם. טוב, נראה לי שרון לנו גם תקשין.
לא, אפשר לשאת אחר כך.
למרות שאני רואה כבר אותה בגלל מה שרון הרבה דברים לעשות היום.
מנורי הזה, כן,
לא, חייב לתת לך מה זה. זה לא באמת עניין של זמן. אני פשוט לא מבינה את זה. זה לא הזמן לעזור. זה צריך לעזור.
שאני קורא ואני אבין, זה כמו הראשון.
אוקיי, יש שלושה נורים, הראשון באמת זה להבין לכתוב, יש שני, ואחד
זה אותו אחד?
לא. הוא אומר שצריך כאילו לשנות כל המקרה לעניין הזה, אבל קשה להבין מה הוא חושב שזה, קשה להבין שזה. אוקיי, קובעים. אפשר לשים כאילו מה נשאר. הבנת את המאמר השני. לא הבנתי את הפואנט. אוקיי. המאמר ההוא שאומר
לא נכון שקונטקסט זה לא...
כן,
זה החלק שהבנתי.
זה החלק שהבנתי. זה לא מה משחקים.
תודה. זה הלך. כן. יש משהו? אוקיי. טוב. אוקיי. התחלנו לדבר, I'm sorry, we started to talk about receptive fields. How do we define receptive field? Excuse me for being late. I was stuck in a traffic jam, and I'm glad you waited. Somebody came and told you that I was coming? Yes. Okay. Thank you. Okay, receptive field. What we want to do today is describe receptive fields and go from the simple definition to the complex one where we might even throw it at. Okay? And the question is, what do we mean? What does it do for us? What is the meaning of receptive field? Okay? So we said last time that receptive field, the first notion of receptive field is where in the world or on the retina there is a change in stimulus will change the activity of the cell we're recording from. Okay? Receptive field always talks about one cell, one neuron. We record from a neuron in the spinal cord, and we show a light, and we ask, does that cell respond? Usually not, right? Somewhere in the brain, yes. Somewhere on the retina, yes. Okay? But one cell. What do we want to learn from it? What do we want to learn from this whole concept of receptive? We've got a cell in the brain. We're recording from it. We now know its receptive field. What did we learn? Yeah.
So one thing is the nature of the receptive field, whether it's spatially organized in some way, whether it's position, speed, color.
And if it is?
So I think you can look at this problem from many different perspectives, but
good. Let's start with one of them. What's one perspective?
The goal is to identify stimulus parameters that drive cells.
We want to know something about cells. So this is one way of defining what a cell is. Why do we want to know what a cell is? We want to know how the brain works. Why do we want to know how the brain works? Well, usually because we want to know how we work. We have a brain, and our brain makes us work, so we want to know how we work. Okay? We said last time that the brain is not like a computer, because a computer has one CPU and the brain has 10 to 100 billion CPUs. What is the brain like? To me, the brain is like a society, like a chevra. There are about the same number of neurons in the brain as there are people in the world. 6 billion, 7 billion already, to 10 to 100 billion. Same order of magnitude, more or less. 90% of the energy that each cell in the brain uses, it uses to maintain itself. 10% is to do its function. Same thing with people in the world. 90% of our energy goes to maintain ourselves. About 10%, hopefully, is used to do something for society. Okay? Another thing about that analogy. The whole is greater than the sum of the parts. which cell in the brain is responsible for my personality? That's ridiculous, of course, no one cell. Which cell in my brain knows who I'm seeing at this moment? No one cell. Well, maybe. But which cell in the brain has consciousness? Obviously not one cell. Okay? Now let's ask about society. Which person in society is responsible for the economy of the country? Hopefully not one person. Which one has culture? Which one has the foreign policy? Which one has an army? One person can be a soldier but not an army. So the whole is greater than the sum of the parts in society, in the brain. So if we want to understand society and how it works, we still have to study each person. Okay? We can look at a society as a whole and try and find out things about it, as we can take parts of the brain and find out what that part does. And that's generally what we're doing with fMRI. But in physiology, we want to record from one cell to know what its share, what its role is in vision, or in whatever that part of the brain is doing. Okay? So that's, we want to know the properties of one cell, not so much because we're interested in that one cell, but we're interested in the function that it plays. Okay? Next thing. So we now know about that one cell. What about all the cells around it? They're doing different things. Okay? So one of the things we'd like to know is the wiring that the brain does in order to create vision. If we know the receptive fields of one, let's talk hierarchy, one layer, and then we can record from the next one, we might be able to derive the properties, the summation properties, that go from layer to layer in that case. Okay? And we might be able to prove that it doesn't work simply feed forward, but there's a much more complicated thing going on. Okay? So one of the reasons for doing receptive field is to know what the interactions are and what the connections are between cells. Okay? So those are two very important things. One, the role of the cell in the function. The second is how it's wired together. So we can find out how the whole thing works. Okay, good. So we want to derive or guess what is the connectivity from area to area. That's one of the functions of doing this research. Okay, good. Receptive fields. Okay, and we started with the limulus, and then we jumped to Ubel and Wiesel, and you've read an article by Ubel and Wiesel, right? So you know everything about it. Okay, and what they did was have a projector and project on the screen a spot and so on, and you've heard the story about their breaking their slide? No. Okay. So this is their slide projector. You guys don't know what a slide projector is because it doesn't exist anymore. Slide projector, you take a piece of film. You don't know what film is. It don't exist anymore. Okay, a piece of film. And on that film, you have a hole in the middle that gives you light going through, or you have a black spot with, okay, and you put that between two pieces of glass, and you put it into the slide projector, and you can project a picture onto the screen. Okay? One of the great innovations of Ubel and Wiesel, and also of Letwin, we didn't talk about the frog's eye, is to project on the screen instead of on the retina itself. Before that, people had projected pictures onto the retina. They said, well, we might as well use the optics of the cat and have the cat look at the screen, and then we can record from the brain. And the cell we're recording from, we're going to find out the receptive field properties of that one cell. Okay? So they went to the LGN, and they used spots of light. They got these fantastic responses. They went to the cortex, and the responses were very sluggish and slow and not very different when they had this spot of light or they didn't have the spot of light. They didn't know what to do. One day, the slide fell on the floor, and the glass cracked. I said, okay, we'll throw away the slide and we'll get a new slide. Well, it's just a small crack. Doesn't matter. It still has this nice black spot in the middle. We can still use it. And they used the slide, and suddenly they got this fantastic response from the cell, and the cell was responding to the crack in the glass because it responds to a line rather than to a spot. Okay? And that's how they found it out. That's their big discovery. Okay. Good. Orientation selectivity. Okay. But let's go back for a moment to lateral inhibition. Now, the best way of demonstrating lateral inhibition is to demonstrate Mach band. Do I have a thing here? Yeah, okay. Let's see if we can get this to work. Yeah. You see this line here? Yeah? No, you don't see it. We'll get another line for you. All right, well, you can see it here. Anyway, I'll point it out here, and then I'll point it out there. You see there's a dark line, and then a bright line, and then it's less bright and less dark. You see it here. At this shadow, the best way... Yes. Yes. Okay. Yep. You see the shadow of the screen. And it's dark. It gets suddenly much darker at the edge, much brighter here, and then less bright. Darker, brighter, and less bright. You see that? It depends on the distance a little bit. That's not there. That's your eyes fooling you. Okay? You don't believe me, I know. You shouldn't believe me because you should believe your eyes. But if you take a physical measurement, it's not there. Okay? And this is what Ernst Mach, famous for Mach, speed of sound. Okay? He also found that when you have a change from darker to brighter to brighter to brighter, you see a dark edge here and a bright edge here at the edge. It's as if the edge is enhanced. And he said, if that's so, and he said that more than 100 years ago, he said, if that's so, there must be something in the eye which is inhibiting what's happening at one point by what's happening around it. So that at this edge, there's lots of inhibition from here and little inhibition from here. In the middle, there's little inhibition from all around. So when we get to the edge, we get more inhibition. That's where we have a dark line. When we're here in the bright spot, when we get to the edge, we have less inhibition, and therefore there's a bright line. Clear? No. So say it again. Okay? Here's another edge. There's an edge going here from bright to dark. And there's a dark bar here and a light bar here. Again, depending on the distance where you're sitting, whether you see it well or not. Okay? And he says it's because here, in other words, the edge, which looks like that, looks as if there's a brighter and a darker here. Okay. How does that happen? That happens by lateral inhibition. This is what Hartline found in his limulus, and which was found afterwards in the frog, and everyone, every eye has it. And how does it work? So, first of all, what happens between the photoreceptor to the bipolar to the ganglion cell? Three major levels of cells in the retina, with horizontal cells here and amacrine cells here, but still there is a straight pathway. First thing is that from the photoreceptors, this is a cone, we can go to two types of bipolar cells, on-center and off-center bipolar. I'll say how it works, but if you don't look at it in the textbook, and if you don't think about it, you'll never get it, because the signs change along the way. Ultimately, we're starting out with a hyperpolarizing signal, but we want to end up with a depolarizing signal so that we can have action potentials going in the optic nerve. So we have to switch somewhere. Okay? And there are two ways we can switch. One is right here from the cone to the bipolar. Okay? And what happens is that when we depolarize the cell, we stop the transmission of neurotransmitter. Okay? What does the neurotransmitter do? We decrease glutamate release in both cases. But the glutamate here was activating the bipolar, and so we deactivate. Here the glutamate was inhibiting, and we stopped inhibition. We do disinhibition. Okay? And therefore, we get here a hyperpolarization, maintaining the sign that we had here. Here we've switched it, the sign, and we got to depolarization. So here it's an off-center cell, and this is an on-center cell. Okay? So the bipolars come from the same kind of cone, and they get two signals. Why should we need both an on and an off response? Why should we use twice as many neurons for information from the retina to the brain? Why isn't one good enough? After all, if the light goes up, then we get a bigger response. If the light goes down, we get a smaller response. This response should be good enough to tell us everything.
Contrast for the edges.
At the edges. Okay. Yes. Something else. What happens to the response over time? We talked about it last time. Adapts. There's adaptation. So if we turn on the light, we get a big response, which then adapts down. Now we turn off the light. What happens? Well, it goes down a little bit. There's not much further down to go. Therefore, we need another neuron, which will give us a big response at off, and then it will adapt. Okay? So we use two signals, one for on and one for off. Okay. Yes, glutamate can do two things. It can either depolarize or it can hyperpolarize to different bipolars. Did you learn about the Dale principle? Well, there was an accepted principle that one cell can only have one type of synapse. A cell cannot excite this and inhibit that because it only can have one kind of neurotransmitter. Okay? A cell is a cell in a cell, and its different axons will do the same thing. But, two buts. First but, it can have not only one type of neurotransmitter, it can have a cocktail of neurotransmitters, and it has to send all those neurotransmitters at all its synapses. Second, the receptor molecules on the synapse can do different things. Acetylcholine does what? Excites or inhibits? Both. It depends where. Depends on the receptor. So that's the same thing that's happening here. The same neurotransmitter, glutamate, does two different things on two different types of bipolar. There's a difference in the bipolar. Okay? It's not that it can send different things. Okay. Then comes the horizontal cell. And the horizontal cell receives information from a lot of photoreceptors. And then it inhibits the transmission of signal from the cone to the bipolar. Whatever the cone is doing to the bipolar, this says do less. Okay? It interferes with that transmission. And since it's receiving information from all over, it's acting as a surround inhibition. So, light gets the photoreceptors to excite the bipolar, but the ganglion cell, the horizontal cell, receives from the annulus all around and inhibits that transmission. This is a electron microscope of, maybe for this we turn off. We won't. Okay. This is the receptor cell. This is the receptor cell. This is the horizontal cell. This is the bipolar cell. Okay? This is an ending of it coming up near the cone receptor. And you can see that in this triad, you can have the receptor, the bipolar, the horizontal, and the bipolar all together. This is exciting this, or inhibiting. And this is interfering. Okay? Clear? Yeah? Okay. one interesting thing here is this ribbon synapse. It's a special kind of synapse. Probably has a lot of neurotransmitter. It allows it to transmit constantly, not like a regular synapse, which every time there's a spike, it gives some transmission and then it stops. Okay. So when there's light in the center, you can get a hyperpolarization. When there's a light around it, you get a depolarization, the opposite signal. Okay. So that leads ultimately, when we go to the ganglion cell, where we get the spikes, when there's light in the center, we get an increase, which then dies down. When there's light in the periphery, we get a decrease in the spike rate. Okay? Center, surround, both. What happens when you do both? It depends on the sum. Which is greater, the center or the surround? Usually, the sum of everything is a little bit like the center. Okay? Same thing again. And that makes the appearance of things depend on what's happening around it. These two are supposed to be the same intensity. And this looks darker than this. This looks bright because of the surround around it. Okay? We see things because of the edges. Okay, David Marr. David Marr said the following. How do we know where there's an edge? Where there's an edge between dark and bright. Okay? So, here is an edge, the blue line, but I've not just taken an edge, I've smoothed it a bit. Okay? Smoothed it around. Let's take the first derivative of that edge. What's the derivative here? 0. What's the derivative here? Positive. And what's the derivative here? 0. So that's the red line. Okay? The red line is the derivative. Okay? Now let's take the second derivative. What's the derivative of the red line here? Positive. What is it here? Less positive. What is it here? 0. What is it here? Negative. Less negative. And 0. So the green line is the second derivative. What happens at the middle of the edge? Nothing. The second derivative goes to 0. It's positive on one side and negative on the other. So the edge is found by what David Marr calls the zero crossing. So if we look for the zero crossings, then we know where the edge is. Why is it important to know where edges are? Because most things we recognize through the edges. Okay? And David Marr said what we do, what the brain does in vision, is first find all the edges, then try and find which edges are important, and then use them to find out what the shape of the object is. Yes?
Can you explain how the mechanism, the eye, infers the second derivative? I can
Yes.
imagine
Yes,
the
yes.
first derivative quite well. I mean, the gradient of the shade. But
That's exactly the point I want to get to. So let's just understand what he's saying, what has to be done. There are two things. We want to take the Laplacian, or the second derivative, of the image. We also want to smooth it with a Gaussian smoothing. This, Gaussian smoothing. Okay? Now, there's a trick. Instead of taking the Gaussian smoothing of the image and then taking the second derivative of that, what we can do is take the second derivative of the Gaussian and use that as an operator on the image. Okay? We take, instead of using the Gaussian as an operation on the image, and then take the operation of the second derivative on what we got, we first take the second derivative of the Gaussian, and whenever we get that, we use that as an operator on the image itself. Now, what's the second derivative of the Gaussian? So, here's a Gaussian, blue line. First derivative is the red. It first goes positive, reaches a maximum, gets less positive at the peak. At the peak, it's 0. It then gets negative. Okay, so the red line is the first derivative of the Gaussian. What's the second derivative? Well, that's the green, the derivative of the red. It's positive. Well, I drew it upside down. So it's positive, and then it reaches a peak, and then it gets less. And at the peak here, it's 0. Then it starts being negative. I drew it in positive, excuse me. And then it goes, okay? So the green line is the second derivative of the Gaussian. Okay, what?
Can you explain what's the x and y axis?
Space, amplitude.
Amplitude of light?
Well, it could be of a signal. In the meantime, we're talking about mass. We're talking about a Gaussian. We're going to smooth the image. The image is going to have intensity. But we're going to smooth it by a Gaussian, meaning, I'm sorry if that's not clear what smoothing is. We're going to take the image, and even though it has a sharp edge, we're going to smooth over that edge by taking an average, a Gaussian average over space. Is that clear? Or if it's not clear, I'll draw you a picture. If we have a signal which is like this, okay? That's the signal. You can't see.
The smoothing operation is taking the convolution of the image?
That's right. Smoothing with a Gaussian means we take the Gaussian, put it here, and what do we get? We get this times this, point by point, and we get a little bit of this. And then we move it over, and then we've got a little bit more. And then we move it over more, and we will get this same shape, but smooth. Okay? Is that clear? Yeah? Why do we smooth? Well, our vision smooths. It has to smooth. Because our receptive fields are not like that. Our receptive fields are like that. Or rather, in the end, they're going to be like that, right? That's a surround. They're smoothing. Okay. So.
Sorry.
Yeah.
Are you now talking about what Ma believed is going on, or what electrophysiologists found is really going on?
I'm going to tell you what he believed is going on, what electrophysiologists found, and why the two correlate.
And I remember from somewhere that Ma said that the reason why there should be smoothing is that there's operations going on several scales of space. Or
Right. In other words, when we talk about finding the zero crossing, okay, we can find the zero crossing. I did it with some kind of smoothing. You can smooth differently, and you'll always find the same point for the zero crossing. When they all come to the same point, then you know you've found a good one. Okay?
okay, but if your smoothing is very wide and you just smooth out the small edges.
That's right. Then it'll be nothing. Exactly. Okay. So the second derivative of the Gaussian looks like what? It looks like negative, positive, negative. Okay? That is exactly the shape of the center surround receptor field. Okay? It is what we call the difference of Gaussians. A Gaussian center, a Gaussian surround, the difference between them. DOG, difference of Gaussian. So it turns out that doing a Gaussian smoothing and then doing a second derivative is the equivalent of doing a multiplication with a difference of Gaussian. That's the point that Marr is making. That ultimately, the brain has figured out a way of just doing summation, just doing integration of signals, positive and negative, and it's the equivalent of the second derivative. and the second derivative is what tells us where the edges are. Okay? Yeah.
Won't the second derivative be 0 also where there's no edges?
Yes, exactly. So therefore, you need a second derivative. You need a 0 which is between a positive and a negative. A 0 crossing. Exactly.
But just one more thing, that this Gaussian is not important at all, right? It could be any bell-shaped.
It could be ME, but yeah. That's only to make the math easy. Okay? So what does the receptive field really look like? Okay? In one dimension, it looks like center surround. It's really a Mexican hat because it's in 2 dimensions. Okay? Okay. Now, if you take an edge and multiply it point by point with a receptive field, you get again the same Mach band, positive and negative, and a 0 crossing in the middle. Okay. Marr talks about 3 levels of discourse. Number 1, there's a computational theory. What is the goal of the computation? Why is it appropriate? What is the logic of the strategy by which it can be carried out? What is being computed and why? For him, in this case, it's the 0 crossing. We want to find where there's the edge. We want edge detection. Representation and algorithm. How can this computational theory be implemented? What's the theory? What's the mathematical process for working it out? What is the representation of the input and output, and what is the algorithm of the transformation? What is the system of representations being used in the algorithm for the transformation from input to output? Okay. Mathematically. And then, finally, the hardware information level. We can do this on a computer, or we can do it using neurons. So we want to discuss all 3. What is the goal of the computation? How do we get to that goal? Okay. We want to find an edge. We do it by 0 crossing. How do we find a 0 crossing? Either in the computer taking the second derivative, or neurons summing up positive and negative from center and surround. Okay. This is the famous Hermann grid. You all notice that there are gray spots at the intersections, but not at the intersection you're looking at. Okay. In this case, you know that it's a illusion, because when you look here, then this one has no gray. And when you look here, then this one has no gray. Therefore, you know there's something happening in your eye and not on the screen. I'm not changing the screen every time you move your eye. Okay? What's the cause of this? I'll tell you what the theory is, and I'll tell you that it's wrong. Okay? The theory is that at the intersection, we have center and surround. There's no inhibition coming from these points. There's inhibition coming from 4 parts of the surround. So there's a lot of inhibition on this one. On this one, there's only half as much inhibition, because there's no light here and here. So this has less inhibition than this, so this looks gray compared to that. Got it? Yeah. What happens at the point you're looking at? Well, in the center of the retina, the receptor fields are smaller. So they're like this. There's no difference between the one that's at the intersection or the one on the edge. And in fact, the ones that are important are not these at all, but the ones which is partially covered and partially not covered by that edge. So you're really finding the edges. And the edges are just as contrasty at the streets as at the intersection. Okay? Now, why do I say it's wrong? I say it's wrong for 2 reasons. Number 1, this is very local in explanation, not global. But if you don't have straight lines, but wiggly lines, it disappears. Okay. Good enough for reason. So it probably has something to do with higher level senses around things, not with the receptive fields at the LGN. It'll take 5 more minutes. Okay. So all these are due to. Okay. Comes along Christina Enroth-Kugel and John Robson. And they say, look, let's think about the visual system as we would any engineering system. How do we test your speakers, your stereo system at home, if it has good sound? You probably don't have stereo systems. They don't exist anymore either, but how do you what? Signal-noise ratio. For what signal? What signal will you use to test it? You'll use a sinusoid. You'll use a pure tone, and you'll try all the tones, and you'll see how well they're transmitted. And you'll get a transmission function for the system. You'll try on very low tones, and ultimately it won't transmit too low unless you have this big woofer there. And very high tones, ultimately it also won't transmit. Okay? And a good system will have a very broadband system, and a poor one will have just the middle working.
So assume that this is all linear?
Yes. So far, it's assuming everything is linear. So let's look at the linear, and then we'll talk about nonlinear. Okay? Okay? So if linear systems analysis, by definition, is we use sinusoids as a signal. We find out which sinusoids are transmitted well and which are not. Okay? Now, why should we think that the brain uses Fourier analysis of the signal that we're seeing? Okay? For 2 reasons. First of all, it might be a good way of doing things. For example, if I see something over here and then it's moved over there, what happened to its Fourier components? Nothing. The phase may have changed a bit, but the amplitude of all the Fourier components stayed exactly the same. So we have a consistent, unchanging representation. What happens when something moves from far away to closer to me?
The amplitude increases?
The
Amplitude is increasing?
No, the amplitudes are not increasing. What is changing? Something which is far, there's a spectral shift. All the spatial frequencies which were higher spatial frequencies when it was far away become lower spatial frequencies when it's close. But the relative spatial frequencies remain the same. So again, it's an invariant representation. So Fourier might be a good representation. It certainly is a good way for testing the system. Okay? Now, I have to be careful with one thing. Fourier, when we talked about the stereo, we talked about temporal sinusoids. Here, we're mixing up. We really are interested in spatial sinusoids. When I said an image is far or close, or an image is moving from place to place, its spatial Fourier analysis remains the same. Okay? So Enroth-Kugel and Robson gave sinusoids to the cell. And what they found was that the cell responded with a sinusoid kind of response, and its amplitude depended on the amplitude of the signal and on the spatial frequency of the signal. So that
the amplitude spikes, or?
Yes, this is very good, thank you. This is spikes per second. Okay. And ultimately, they found this kind of response. For low spatial frequencies, there was a kind of constant response. When we got to middle ones, we got a bigger response. We got to very high spatial frequencies, we get to lower responses. Why should this be? let's remember that we have a receptive field which looks like this, center surround, or like this, center surround. Okay? So, when the center of the receptive field is exactly the right size for the sinusoid, then we get a very big response. We turn the light on here, this responds. We turn the light off here, this goes off. When the spatial frequency is higher, then we have thinner bars. We're turning the light on here but off here. So we get less response. Ultimately, we'll get so high that we'll be turning on and off about equally over the center, about equally over the surround, and we'll get no response. When we go to lower spatial frequencies, then the light on is going also in the surround, the off surround. So therefore, we get a reduced response. Okay? Clear? Yes.
Shouldn't there a lot of variability in the response of one shell because of the way the grid is aligned with respect to the center?
That is exactly.
Error bars here.
Yes. If you place it perfectly, like I did in that slide, then you get a big response. If you place it halfway, so that the bright bar is half on the, then you get no response. That's exactly the point. Okay. So these are cells which they called boring cells or X cells. They're linear. They add up the light in the center and the surround linearly. There were other cells where this didn't work. Yes, which they called Y cells, where sometimes there were two peaks at on and on off. Sometimes there was one peak. Sometimes there were two peaks which were of different size. There was a variability. They knew that something was wrong and something was nonlinear. And they didn't know exactly what. Okay? We'll hold a 5 minutes break. You had most of it before. No. 5-minute break, and then we'll go on to the cortex, and we'll see what nonlinearity does. go to the cortex. To go to the cortex, we have to leave the eyes, follow the optic nerves and the optic chiasm so that we get to the LGN and from the LGN to the cortex. Okay. The important thing to remember is that everything on the right side of the eye, which sees the left side of the world, goes to the right side of the brain. The right side of the other eye, which sees the same left side of the world, also goes to the right side of the brain. Okay. Why is it good that the right side of my brain sees the left side of the world rather than seeing the right side of the world? What else is crossed over? Everything. So if you're going to cross over, you want to cross over everything. So the right side of the brain sees my left hand and also controls my left hand. And the left side of the brain sees my right hand and controls my right hand. And if I move my hand there, this way, and I try and do things, it's not as easy. Try and play the piano this way. Okay.
So, but is there a reason why everything is crossed?
Is there a reason why everything is crossed? I don't think that there's an evolutionary advantage to it, or at least I don't know it, but there's an embryonic reason for it. In other words,
It's either in the development process?
in the development process. I don't know if it's easier, but that's what happens.
And is it the same in all vertebrates?
I think it's pretty
all mammals.
ubiquitous. All mammals have it.
But other vertebrates?
I think they do, yeah. Now, I'm hesitating because audition is different because of the 2 ears, but there are many more musculim, and you're going to get to that. You can ask Ellie or Adi, whoever's going to teach it. And I'm thinking also about birds and fish have eyes on the sides of their head, and therefore see 360 degrees. And I don't know for which degree it's... Okay, good. Okay. And therefore, there's always an interesting question to ask, what happens if you cut here, or cut here, or cut here, or cut here? Which parts of the visual field do you see in which part of your brain? And you can work it out. Okay. There are in the geniculate, it's called geniculate because it's like the knee, genie, genou in French, okay? So it's bent over like that, it's folded like a knee, that's why it's called geniculate. There are 6 layers, and the 6 layers are divided between the ipsilateral and the contralateral eyes. In other words, information is not united at the geniculate, it's only united at the V1. However, they are aligned, so if you put an electrode through this way, you get more or less the same position receptive field in the world. So half the work is happening here, but the other half is happening here to coordinate. Okay? And there are 2 kinds of cells in primates, monkeys and people, magnocellular and parvocellular, which are not exactly the same as the cat X and Y cell. In fact, the X and Y cells are probably both magnocellular type, and the primate adds on the parvocellular neuron pathway. And the parvocellular has to do with color vision and so on. So these are much smaller receptive fields than the magno, and they have to do with things like color vision rather than things like motion perception.
Cats don't see color?
Cats don't see color. They sacrifice color for intensity, and therefore they see very well in twilight when they want to catch their prey.
This is excitatory cells only?
There are inhibitory cells within the geniculate, changing the receptive field, but the transmission from eye to geniculate and from geniculate to V1 is all excitatory. Okay? The principal cells are excitatory. Okay? And this is a microscope showing the layers. between the parvo and the magno. In terms of spatial frequency, you can't see this, I know. Spatial frequency, the parvo have a higher spatial frequency cutoff than the magno. In terms of temporal frequency, it's the opposite. The magno see faster things than the parvo. And then from the layers of the geniculus, we get into the V1, where, as you know already, there are bands of left eye, right eye, left eye, right eye. Okay. So we have columns where all the cells deal mainly with the left eye or mainly with the right eye. Near the border, this picture is very bad because it shows as if there's a sharp border. It's not a sharp border. We have pure right eye mixtures going to about half-half, mixtures where left eye is more to pure left eye, and so on. So there is a constant mixing going on. Okay. And the place where they go to is different parts of the layer 4. Okay. Layer 4 is the recipient of all the information coming from the eye, but it goes to different layers within layer 4. The cortex is like a chip. We can use the same chip to build a computer or to build any other kind of electronic device. Okay? So we can use the same chips for doing audition or vision or motor control and so on. The chip is the 6 layers of the cortex. What exactly they do, we don't know. They probably do different things in different areas. But there are always 6 layers. Well, the anatomists tell us there are always 6 layers, but then they go on and they say, well, but in this case, layers 1 and 2 are more or less together. And layer 4 is divided up into 5 parts. But still, there are always 6 layers. Okay? So, don't entirely believe it. So we have these pathways coming up. And what I wanted to get to was orientation selectivity. And Hubel and Wiesel, that's what they found with this slide with the crack, that when the orientation was along the receptive field, they got a lot of spikes, and when it's wrong, then they get less and less, and going the other direction, they get less and less. So they found cells with orientation selectivity, and again, there were columns of cells which all have the same orientation preference. Now, Hubel and Wiesel, the way they worked, as you saw in the picture, was they put the cat in front of the screen, they took this slide projector and moved around the thing. Well, while they were looking at the screen and doing this and writing on the screen what the receptive field was, they couldn't look at the oscilloscope which was recording the spikes. Okay? So in order to do that, what they did is they attached the oscilloscope to a speaker and they listened to the spikes. So they had shh, they did over here, nothing, nothing. Shh, now they changed the orientation, nothing. Shh, and then they drew the receptive field. Okay? Good. There's only one problem. What happens if you're recording from 5 different neurons? Then you get shh. Okay? So you're getting the average of the 5, or the sum of the 5. Okay? That's what they were doing all the time. They were recording from multiple units and not getting pure receptive fields of one cell. So they mixed everything up. And therefore everything looked very smooth. As they were in one area, they all responded to more or less the same orientation, because they were averaging from a number of units. And then they gradually moved along with their electrodes, and they got gradually changing receptive fields in terms of which eye and in terms of orientation selectivity. Okay. And then they defined the hypercolumn. You got the concept of hypercolumn? Hypercolumn is the area of cortex, something like a half millimeter square, which has both eyes, right and left, and has all the orientations going around the clock, 180 degrees. Why 180 rather than 360? Because the line this way and this way are the same. Okay. Of course, if it has direction selectivity, then it might be different. Okay. Anyway, so you have all the orientations, all the ocular dominance in one cube. So that's 2 dimensions. Orientation and ocular dominance. What other dimensions are represented in V1?
Direction of movement, speed of movement.
Okay, so motion. Okay,
Color.
I'm going to put off motion for a moment. What else?
Color shape.
Color shape. Okay, so for color, since they were working first with the cat, there was no color. Then they moved to the monkey, and the monkey was exactly the same as the cat. Why? Because they assumed it would be exactly the same as the cat. And then they finally discovered that there were some areas, more or less in the middle of each one of these hypercolumns, which had color selectivity, and which they claimed at first were not orientation tubes. They found these areas by a certain staining technique, cytochrome oxidase. These cells did respond to the cytochrome oxidase, the other ones didn't, and they were not orientation tubes, they were color selective. So color is in separate areas. That's not recognized today as being completely so. Probably there are cells which are both orientation and color selective. Okay, so we have motion, color,
Shape.
shape. Okay, what do you mean by shape? By shape, what we mean is position in the world. So you have a hypercolumn which sees everything happening in one position in the world, and the neighboring hypercolumn sees what's happening in the neighboring position. And you keep going. So there's a map of half the world in V1, half the world, okay, by hypercolumns. There are about 100 by 100 hypercolumns, about 10,000 hypercolumns. Good. So we got that. Now, how do we get orientation selectivity? Here is Hubel and Wiesel's model. You take a number of LGN cells and sum them in a simple cell, and the simple cell has a center and a surround. And when you put a bar this way, it responds. When you put it this way, it goes into the surround and it doesn't respond. Okay? That's their model. This is from Miro and Greenwald, who used dyes which he put on the cortex, and they're voltage-sensitive dyes, and therefore you can see which cells are responding. And when he puts a bar in this orientation, then all the red things are, and in this orientation, and the yellow, and so on. So you get this nice map. And in particular, what's interesting is that you get a pinwheel, what he calls it. In one spot, going around it, you have all the different orientations.
Which organism is it?
Which?
Is this a rat?
It's monkey.
Monkey. Great.
Okay. This is orientation selectivity again. And now, after we've got these simple cells responding to the barbed light, and you can have all kinds of organizations of center surrounds and so on. Although once you get to this kind of a division, we don't know exactly where the center and the surrounds are. Maybe these are the centers and the surrounds are outside, and so on. So it becomes non-clear already whether the orientation tuning is done by center surround, or maybe there's centers like this and off centers on the two sides. And then they talked about the complex cell. And they said, well, the complex cell is very simple. All we do is we have many simple cells. You've done this, right? Many simple cells, and they sum together and you get a complex cell. Is there any problem here? Well, I'll tell you what the problem is.
This is like a theory, right? It's not measured. This is like an explanation.
What's measured is the response of the complex cell and response of simple cells. The theory says, how do you build up the complex cell? That's theory. Okay? And we have to know that the basic thing of Hubel and Wiesel is feed-forward, is hierarchy. We go from retina to geniculate to simple to complex to hypercomplex to grandmother. Okay? That's how things work. And Marr agrees. Marr also talks about feed-forward. Okay? They're both wrong. So let's just talk a moment about why I say there's something essentially wrong here, and which you have to be ready to confront. And it is the following. I don't know which of these works, but maybe the reduction. So here we have a simple cell which responds to a bar of light here. And then we have another simple cell which responds to a bar of light here. And these two simple cells send their outputs to the complex cell, who sums the two of them, right? So, what happens, according to Hugo Weasel, since this is center surround, if I have a wide bar, this simple cell does not respond. And if I have a wide bar, this simple cell does not respond. That's why the complex cell does not respond to wide bars. It only responds to narrow bars, but it doesn't matter where the narrow bar is within the receptive field of the complex cell. Right? That's the theory? Clear? Now I ask you, how much is 1 plus 1? 0, right? 1 plus 1. If I have a bar where there's a response, and there's a response in the complex cell. If I have a bar here, this cell responds, and this responds. If I have two of them together, 1 plus 1, the complex cell does not respond, 0. Something's wrong. Well, it's obvious. Since you have a wide bar, this one doesn't respond. For a wide one, this one doesn't respond. So what's the problem? In other words, when you think in terms of pictures of cells, you can do anything. This one responds, it doesn't respond, this one. But if you think mathematically, 1 plus 1 has to be 2, not 0. There's something wrong here. Okay? There's something essentially non-linear about the complex cell. Hugo Weasel never thought in these terms. If you look at their papers, there are no graphs. That's not true. There is one graph. There's one graph in the Hugo and Weasel papers, which is position and orientation, and you have something like this. Okay? That's the only graph they have. How orientation changes when you move in position. No graphs, no numbers, nothing. Nothing with real numbers. Okay? There are some people who say if you can't measure it, it's not science. Science is only about things you measure. So what is the answer, though? Okay, I've asked the question, I've asked it quite strongly, okay? But what's the answer? How do we understand it? What's happening? Where's the difficulty? Yeah.
Doesn't it cancel out to be 0?
It cancels out, yes, but how does it cancel out? Why does one work and the other one doesn't work?
Because the non-receptive field cancels out with the receptive field of black, so it becomes 0.
So we have, if we put a bar of light here, what's it doing? It's exciting these cells, and we get this cell excited. But what's happening to this cell when we put a bar of light here? It's inhibited, because this cell has its thing here. So therefore, if we put a bar only here, this should have given us +1, and this one should have given us -1. And when we do a bar of light here, we should have had it the other way around. So it should have been 0 all the time. Okay? Is this problem clear? Some of you say yes, some of you say no. Let me say it again. If I put a bar of light here over the centers of the LGN cells which comprise this simple cell, then I get a positive response from this one, but I should be getting a negative one from this one. And when I move it here, then I should have negative from this and positive from that. And when I do them both, then everything, each one of them should be zero. Okay. So the answer is that complex cells are nonlinear. And the only way to understand this is that the complex cell sums up not the response of the red cell plus the response of the black cell, but it first takes the absolute value. Well, absolute value is not the right thing. What I really want to take is the half-wave rectifier. It only transmits plus and minus. It only transmits the positive part. So what I really have to write is R plus minus something like that. Is that right? The two? If it's negative, R. What do I have to do? R. I want to get positive when it's positive and zero when it's negative. So if this is negative, so I want what?
Parentheses like this and subscript.
Then any notation you need, right?
Yes. If this is negative, then this will be positive. This gives me only negative, so I have to take minus R and...
No, minus you should go outside first.
You
What?
did it already.
Anyway, I've said it. Okay. Got it?
Yes.
We could do it. Yes.
How do you know that that's what the complex cell
Really
that,
does.
that's what I think. Maybe it's maybe that's just how the simple cell output.
Oh, sure. It could be. You say the simple cell output could be like this.
Only positive output.
Fine. That's fine. On the contrary, I prefer that. It's the simple cell which only puts out a positive signal. In other words, cells which are depolarized give out spikes. Those which are hyperpolarized don't give out anything. That's exactly right. Okay. So we don't know where it is. Somewhere between the simple and the complex. Now synapses do that. That's what synapses do. They only transmit positive signals. So it's clear. No problem. Synapses are nonlinear. It's strange things which sum linearly. You have to work hard to make things linear. Yeah.
So, but everything you said now works only if these cells have a baseline firing rate of 0, right?
That's right. But since we had an adaptation, baseline firing is always going to be near 0. Yes, if you take a stimulus and you put that stimulus there all the time, then on top of that you can get positive and negative. That's right. That should be it. Okay? Okay. Now we can go back to the Y cells, which are also nonlinear. We can try and understand this. Okay. So in the retina itself, there are cells which are nonlinear. This is work I did a long time ago with Bob Shapley, with my postdoc. And what we found was, again, that the X cells were linear, either positive, negative to the two phases of a stimulus, or 0 if you put them exactly in the middle of the receptor field. While the Y cells sometimes had one peak, sometimes had two peaks. You know, I don't know, on-off cells were found before, in the frog's eye, in the rabbit eye, and so on. The question is, what does that mean that a cell responds either when you turn on the light or you turn off the light? That seems silly. I mean, if you can't even tell the difference between light and dark, what can those cells be telling the brain?
Does it just
Change. Exactly. They're changed. Something is happening. And it doesn't matter which way it's happening, but something's happening. Be aware. Go and look. Okay? Use your linear cells to find out what's happening, but first of all, be aware that something's happening. So if there's a flash over here, I immediately go and look there. Okay? Okay. So something's happening. That's what Y cells are telling us. And ultimately, what we did, Bob and I, was to look at low spatial frequencies and high spatial frequencies for the X cells, low spatial frequencies and high spatial frequencies for the Y cell. And it turned out that the Y cell at high spatial frequencies were always double peaked, and it didn't matter what the phase was. What I'm saying is, let me just make sure it's clear. If this is the receptive field of the cell, we said that if we turn on the light, turn on here and off here, then there'll be no response to the X cell. In the Y cell, you get a response here also. And if you do high spatial frequencies, in other words, lots of bars, instead of going away, you get a two-peaked response, and it doesn't matter where you place them. That's amazing. If you go to low spatial frequencies, then you get mainly one peak. Obviously, when the grading is over the center. And when you go 90 degrees away, well, all of a sudden it's two peaks again, instead of being zero. And 90 degrees from that, then you get off instead of on. Okay, that's fine. But why do you get double peaks? So we said maybe there are two parts to the response of the Y cell, a linear part and a nonlinear part. The nonlinear part is irrespective of spatial phase. And when the linear part is zero, that's the only part you see. So we can take this and add it to a linear part. Subtract this from all these responses, and you get the pure linear part. So the receptive field looks like this. There's a linear center and surround, and there are lots of subunits. And since they're placed randomly, it doesn't matter what the phase of the sinusoid on it is, one of them will re-respond when you turn it on, and when you turn it off, you're getting the other phase that the other one is responding. So on, off, any one of them will respond. Okay? So the Y cell has exactly the same kind of nonlinearity as the complex cell, in that it's summing things non-linearly in terms only the positive aspect and not the negative aspect. Okay? So this happens again and again. And in fact, we found in V1 cells where there were like two LGN cells, or maybe two lines of LGN cells responding and adding together non-linearly. So if you turned on a light here and off a light here, then you got the best response because it was one on and one off. And that is exactly for zero crossing. So there actually are cells which do this, finding the peak here and the null here. Okay, that's the non-linear aspect of Y cells. Okay. Mappings to the cortex. Position we talked about, eye of origin, orientation, complexity, simple to complex. Now, I would say that it's still in doubt whether simple cells feed into complex cells. There have been studies which show just the opposite, that complex cells feed into simple cells. It's unknown to this day. We're more than 50 years after Jubel and Wiesel's study, and yet we still don't know if it's true that it goes simple to complex. It looks like there's a very basic orientation tuning that happens, but then lateral inhibition between cells with different orientations cause the very sharp orientation tuning, not the summation of a very long line of LGN cells. Depth. How do we see depth?
Can I?
Yeah.
So why did Jubel and Wiesel think that this
Bugle and Weasel thought that the retina feeds to the LGN, and the LGN must feed to the most simple kind of cell that they found, which was the simple cell, which must feed to complex, which must feed to hypercomplex. Now, hypercomplex were end-stop cells. Did you get to that? No. Okay. They found another type of cell which they called hypercomplex, which responded to corners. You see that? That's part of their theory. First, you'll see spots. It's sort of a black and black this one. First, you'll see spots. Then you'll see lines, and then you'll see a line irrespective of where it is, and then you'll see corners. Why a corner? Because they found cells. I have stuff on this. Let me get it. These are the complex. And then suddenly they said, well, what about hypercomplex? Things that will respond best when there's a corner. Okay, like here, on the edge. So they respond to this line, but only when it's at the edge. When it's not at the edge, they're not. Okay? They call that hypercomplex. Well, then and because it's simple, complex, hypercomplex. Then they change their mind and they realize that it's not so. Because what it really is, it's responding to this line, but with inhibition coming from here. So if there is a line here, then it's inhibiting the response. There's what they call end stops. The line at the end of it, if it doesn't stop there, then the continuation of the line inhibits the cell. And they found that for simple cells as well. So if they have end-stop simple cells, then they could no longer call them hypercomplex. So Bugle and Weasel went back on their title. But their idea was that you would see a square by seeing how a LGN cell responds to it, how a simple cell responds to a complex cell, and a hypercomplex cell. Okay? That's the question right here. I wrote hypercomplex. Okay. Yes, one more thing about the end stop. If this is the stimulus, the cell responds. If the stimulus is wrong, it does not respond because there's inhibition coming from these two blue areas. If it's a curved line, then it stimulates this. This does not do the inhibition, so there's less inhibition here. So an end-stop simple cell becomes a curvature detector. You can tell if the line is curved or straight.
Why there's less inhibition in this case?
Because this area is also orientation dependent. And it responds and inhibits only when it's in the same orientation as that, and not when it's different. Okay. Let's talk a moment about depth. How do we perceive depth? Five ways we perceive depth. How do I know that you are closer to me than you? Yeah.
Distance measured by either eye,
Distance is measured by
relative shapes, possibly contrast between shapes.
I look at your face, I look at your face. How do I know that she is sitting closer to me than you are?
Size of the shape and your vision of the size of that shape.
Say it again.
Size of the shape and you type
Size.
balloon shape.
So the first thing is size, okay? Now how do I know that she's not a real person and you're a doll, but you're at the same distance? Experience. I assume that you're all people, okay? Your face is twice or three times as big on my retina as his face. And yet I assume you're all the same size. Okay? As I walk back and forth, the size on the retina changes, but you don't appear to change at all. Okay? So somehow I interpret size to be distance, and distance to become size. And there is always this dichotomy, I'm not sure of which one is which. So that's one, size. Next.
Spatial alignment, so things that cover everything have to be closer than things that are covered.
Okay, covering. So yes, covering. Whatever covers my hand is in closer to you or further than you than my face. closer because it blocks my face. This way, it's further away. Next.
Converging lines can be the
Okay. Linear perspective. Linear perspective means that what's far away looks smaller than what's closer. And whatever is on the floor gets smaller and smaller. Whatever on the ceiling gets smaller and smaller. But beyond that, whatever's on the floor moves up. Whatever on the ceiling moves down. Whatever on the walls move closer. Okay? This perspective. Okay? This is more or less the same thing as size, that as things get further away, they get smaller on the retina. Not exactly the same. Okay. It took artists till the Middle Ages, till the Renaissance, to be able to work this out correctly. All the lines meet at one point at infinity and things like that. Okay? Why do things on the floor go up and things on the ceiling go down?
Horizon is somewhere in the middle.
The horizon is somewhere in the middle. Where's the horizon?
נקודת מגוז,
I
לא?
know.
What?
It's called נקודת מגוז בעברית, I don't know.
Magos.
Where the lines meet in the
Yeah.
middle. I don't know.
Why is there a place where the lines meet? On the horizon. No, there was one eye as well. All these are monocular cues. Why is there such a thing?
Light comes down.
Why do things go down from the ceiling?
Brightness.
No. I don't think right.
The angle of the light comes. That's
Yeah. It's the angle of my eye to the object. Okay? The thing that's closer, I have to look up. The thing that's further is further down. The thing's on the floor, okay? Now, what is the middle? That's where my eye is. Okay? The things straight away don't change height with distance. In fact, if you see a picture of the road going there, and there's a tree by the road, and another tree further away. Okay? Now, I didn't draw it right. Well, how should I have drawn it? I should have drawn my eye height to be at the same height for the two of them. And the percentage of tree above and below my eye height are the same for close and far. The size gets smaller as it gets further away, but where my eye is, it should be the same percentage. Okay? Okay. Perspective. What other cues are there?
shadow.
Shadows? Yeah. Next.
There are binocular cues.
There are binocular cues. Okay. Okay, let's do binocular. I would rather do one before we do the binocular. And that is, how do you know with a camera? Well, now you use all electronics. How does the camera know how far away the things are? Focus. So how does focus work?
Contrast not.
Not focus. The things that I'm looking at and I focus my lens to are in focus. Things which are further away or closer are not in focus. So I can use the focus of my lens as a rangefinder to find out how far away things are. Yes.
Isn't this mostly driven by the binocular clue of vergence sometimes?
There's also vergence. So there's focus
And isn't the focus
and there's vergence.
Isn't it a consequence of the vergence?
Well, there are three things which are yoked together. Focus, vergence, and pupil size. Accommodation. Okay? The three are yoked because when we look far, then our two eyes look straight because coming at infinite distance is going to be, they'll meet. Second of all, the focus, the pupil will get small, so have sharp focus. And third of all, our focus to infinity. And when I look at something closer, then the eyes go together, and there's vergence, and the focus gets to something close, and the pupil gets bigger. Okay? If you don't believe me, try it with each other. Okay? You look at the eyes, tell somebody to look far or close, and see what happens to the eyes. Okay. You can't do it yourself. Good. Okay, so these all depend on muscles of the eye. Okay? All these are monocular cues, except perhaps the vergence, which is two eyes together. Okay? Now, what about stereopsis? What cue is that? How do we use two eyes to know how far away something is? Clear? Here are the two eyes. And we're looking at this point. Where does this point fall in the eyes? You're right, say it.
Well, if you're focused, then on the same spot, but
I'm looking at this spot, so where does it fall? The fovea.
right.
It falls in the fovea, okay? Okay? Now what about something which is a little bit over to the right? The blue doesn't work, right? We'll use the black. The black doesn't work. Green. Green. Where does that point fall? Well, by geometry,